Something is awry in our understanding of the universe. Cosmology seems to be heading for a showdown on one of its most basic questions. How fast is the universe expanding? For more than a decade, two types of measurement have been in disagreement. Observations of the current universe typically find the rate of expansion, called the Hubble constant, to be about 9% faster than predictions based on early universe data. Researchers hoped that James Webb, the most advanced telescope ever built, would help to settle the question once and for all. But consensus has so far failed to materialize. Instead, the Supreme Observatory has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. The new physics needed to modify or even replace the 40-year-old theory is now a topic of debate, an exciting and interesting possibility that there's something we don't understand about the universe. Join us as we dig deep into how new ultra-deep images from James Webb just confirmed there is something seriously wrong with our understanding of the universe. Our universe started with a bang, the Big Bang. Energy, mass, and space flashed into existence all within a fleeting instant. Then, the young cosmos formed, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma mirror should have consumed each other entirely. But scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high-energy density of the early universe's crowded content stretched spacetime, pulling a small fraction of this matter safely from the fray. As the universe inflated like a balloon, the standard story of ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies, connected together by a vast cosmic web. Initially, as the universe's content spread out, its energy density, and therefore its expansion rate, decreased. But then, roughly 5 billion years ago, galaxies began to recede once more, at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant and inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped, while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. But here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them. Measuring the universe's expansion takes a little bit more than a radar gun. The first method to measure this growth looks at the so-called cosmic microwave background, CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump as the universe exploded outward. This soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter, and a value for the cosmological constant or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will retreat from us and us from it at 67 kilometers per second. At 20 megaparsecs, This recession grows to about 1,340 kilometers per second and continues to grow exponentially from there onward. If a galaxy is any further than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables. Dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors. According to the standard picture of cosmology, the inflationary vacuum had a super-high energy density and repulsive gravity, causing it to expand. In common with all things quantum, this vacuum was unpredictable. At random locations, it decayed into ordinary, everyday vacuum. The tremendous energy of the inflationary vacuum had to go somewhere, and it went into creating matter and heating it to a blisteringly high temperature, into creating Big Bangs. Our universe is merely one such Big Bang bubble in the ever-expanding inflationary vacuum. Remarkably, this whole process could have started with a piece of inflationary vacuum with a mass equivalent to a bag of sugar. Conveniently, the laws of physics, specifically quantum physics, permit such matter to pop into existence from nothing. Of course, the next obvious question now is, where did the laws of physics come from? In 198, German mathematician Emmy Noether shed light on this. She found that the great conservation laws are mere consequences of deep symmetries of space and time, things that stay the same if our viewpoint changes. A striking property of such symmetries is that they are also symmetries of the void of an entirely empty universe. So maybe the transition from nothing to something was not such a big deal. Maybe it was simply a change from nothing to the structured nothing of our galaxy-filled universe. But why did the change happen? The American physicist Victor Stenger pointed to the fact that as the temperature drops, water turns into structured water or ice because ice is more stable. Could it be, he speculated, that the universe went from nothing to structured nothing because structured nothing is more stable too? Why is there a monster black hole in the heart of every galaxy? There are about 2 trillion galaxies in our universe, and as far as we know, almost every one contains a central supermassive black hole. They range in size from monsters weighing almost 50 billion times the mass of the Sun to the 4.3 million solar mass tiddler known as Sagittarius A** in the core of our Milky Way. But how they got there is one of the great unsolved mysteries of cosmology. We know that a stellar black hole forms in a supernova explosion, in which the core of a star implodes. But nobody knows how a supermassive black hole forms. For years, astronomers have been trying to catch one in the act. But the furthest anybody has got is to discover one forming. The mystery of the expanding universe and its fundamental components continues to intrigue and challenge astronomers and physicists alike. At the forefront of this quest is the Hubble constant, a critical measurement that quantifies the rate at which the universe is expanding. This parameter not only helps us understand the past and future of our cosmos, but also reveals deep insights into the nature of dark matter, dark energy, and the evolution of galaxies. Recent advancements in observational astronomy, particularly with instruments like the James Webb Space Telescope, JWST, have sharpened our view of the cosmos. JWST's ability to peer into the distant reaches of space has provided unprecedented clarity on cosmic phenomena that were previously obscured or poorly understood. However, This enhanced vision has also underscored discrepancies in our current models of cosmology, prompting a reassessment of fundamental assumptions. One of the most pressing issues confronting cosmologists is the persistent discrepancy between different methods of measuring the Hubble constant. Observations from the early universe, such as those derived from the cosmic microwave background (CMB) by missions like Planck, suggest a Hubble constant of around 67 kilometers per second per megaparsec. This value is derived from the imprint left by the CMB, which serves as a snapshot of the universe just 380,000 years after the Big Bang. In contrast, measurements based on the local universe, using techniques like observations of Cepheid variables and type Ia supernovae, yield a higher Hubble constant, typically around 74 kilometers per second per megaparsec. This tension between early and late universe measurements has persisted despite increasingly precise observations and sophisticated analyses, indicating that our understanding of cosmic expansion is incomplete. The implications of this discrepancy are profound. Resolving the Hubble constant debate could necessitate revisions to the standard model of cosmology, which posits a universe dominated by dark energy, approximately 70% of its energy content, dark matter, about 25%, and ordinary matter, 5%. Dark energy, in particular, is thought to be responsible for the accelerated expansion of the universe observed in recent cosmic history. However, the nature of dark energy remains enigmatic. Proposed explanations range from a cosmological constant, akin to Einstein's lambda, to more exotic theories involving modifications to Einstein's theory of general relativity or the existence of additional fundamental forces. Understanding dark energy is crucial not only for cosmology but also for fundamental physics, as it challenges our understanding of vacuum energy and the nature of spacetime itself. Meanwhile, dark matter continues to evade direct detection, despite its gravitational influence on visible matter and light. The existence of dark matter is inferred from its gravitational effects on galaxies and galaxy clusters, which suggests the presence of substantial unseen mass. Various candidates, such as weakly interacting massive particles, WIMPs, or axions, have been proposed, but conclusive evidence for any specific dark matter particle remains elusive. The study of galaxy formation and evolution provides another window into the universe's history and composition. Galaxies are not static entities but dynamic systems that evolve over cosmic timescales. Understanding their formation requires tracing the distribution of dark matter, which acts as scaffolding for the gravitational collapse of gas and stars into galaxies. Observations with telescopes like the Hubble Space Telescope, HST, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have revealed intricate details of galaxy formation across different epochs. These observations show that galaxies grow through mergers and accretion of gas from the intergalactic medium, processes influenced by both dark matter and dark energy. The role of black holes in galaxy evolution is also a topic of intense study. Supermassive black holes, millions to billions of times more massive than the Sun, reside at the centers of most galaxies, including our own Milky Way. These cosmic behemoths are thought to play a crucial role in regulating star formation and the growth of galaxies through processes such as active galactic nuclei, AGN, feedback. AGN are powered by the accretion of material onto supermassive black holes, which releases vast amounts of energy and can profoundly affect their host galaxies. This feedback mechanism is believed to heat and expel gas from galaxies, thereby regulating star formation and shaping the galaxy's structure over time. Understanding how AGN feedback operates requires detailed observations across multiple wavelengths, from X-rays to radio waves. The study of exoplanets, planets orbiting stars outside our solar system, has also revolutionized our understanding of planetary systems and the potential for life beyond Earth. Techniques such as the transit method and direct imaging have allowed astronomers to detect thousands of exoplanets, ranging from gas giants to rocky terrestrial worlds. The discovery of exoplanets has raised profound questions about the prevalence of Earth-like planets and the conditions necessary for life to emerge. Missions like NASA's Kepler and TESS, Transiting Exoplanet Survey Satellite, have identified numerous potentially habitable exoplanets within their star's Goldilocks zone, where conditions may be suitable for liquid water and, potentially, life as we know it. Future missions, including the James Webb Space Telescope and the European Space Agency's Plato, planetary transits, and oscillations of stars mission promise to further expand our knowledge of exoplanetary systems and their diversity. These missions will study exoplanet atmospheres, compositions, and potential biosignatures, bringing us closer to answering the age-old question of whether we are alone in the universe. In conclusion, the study of cosmology continues to be a frontier of scientific inquiry, driven by technological advancements and theoretical innovations. From the origins of the universe in the Big Bang to the nature of dark energy and the evolution of galaxies, each discovery opens new avenues for exploration and challenges our understanding of the cosmos. As we unravel the mysteries of cosmic expansion, dark matter, and exoplanetary systems, we are not only gaining insights into the fundamental laws of physics, but also exploring the vastness of our universe and our place within it. The journey towards understanding the universe's complexities is ongoing, and each new observation brings us closer to a more complete picture of the cosmos and its origins.